Hello guys, hello again. So now we're gonna solve the problem of the ice cube. I'm not sure, is it the second or the third question I sent to you? But anyway, so in this problem we have a cube of ice which is placed on a ground and we want to study the pressure it exerts on the ground. So here we have, they're saying like the mass of the cube, of the ice cube is 3 is 3.7 gram. It's in grams. So I have to change it into kilograms. You have two ways to do so. And I will go with this one, which is you just times it with 10 to the power minus 3. And now it became kilogram. You know, you can do the other way, which is 3.7. You don't do this. You just divide it by 1000 and you will have 0.0037 kilogram. Both are correct, but I'll just go with this one because I will keep the calculation all at the end. Anyway, so this is I'm done with the conversion thing. Yeah, let's go with the it is area of contact with the ground is, so the area is 2.6 times 10 to the power minus 4 squared meter. Thank goodness we don't have to convert anything here. So calculate the pressure the ice cube exerts on the ground. They're asking about P, the guy, not Rho, the lady. And now we know that P in the solid state, for the solid objects, it is F over A. It's the force applied or acts on a certain area, right? So the force here, the force that this cube is exerting on this ground is its weight. It is the weight. So the weight is equal to what? For area, it is mg over A. M is here. So we're just gonna take it from here and put it here. And we're gonna times it with G. G, as I told you before, in your book this year at least, it's always 10 meter per second squared. Yes. So we times it with 10, and this is the area. Just take it from here and put it here. 2.6 times 10 to the power minus 4. And you do your math. And it's going to be, at the end, it's going to be 140 Pascal. The unit to measure the pressure is Pascal. Remember pp? So now we're done with that part. Let's go to the second part, which is the ice cube melts and it becomes water. Now water has a larger cross-sectional area with the ground. As you can guess, it doesn't have a shape. So when it doesn't have a container to collect it together, now it's all spilled all over the ground. So more pressure, more area for it. So what do you think is going to happen to the pressure? Pressure is directly related to the force and to the area, but it's inverse proportion with area. Don't forget this one. P is equal to F over A. So here, those two, they are in an inverse proportion, not the direct one. It is with the direct one with the force, but not with the area. So the area becomes larger now that the ice cube has melted. So the pressure of the ice cube decreases. But I need to explain a little bit more, right? So the cube, let's write it that way. The cube of ice before and after melting has the same weight. So it has the same weight, but this is the important part here. But after melting, let's say, after melting, يعني the water, I'm talking about the water, what's gonna happen? The water has, but after melting, the water has a larger area, a larger cross-sectional area. So it will have, exert or anything. It will act with a less or smaller, let's say it will have smaller or less pressure, P. So I just wrote it that way. You can write it whatever you want, however you want it. Just make sure that you mention 2 points. Number one is that the weight or the mass of the cube before and after melting, when it's ice and when it's water, it's the same. Nothing has changed with its mass. We didn't touch the particles. However, what has changed is the cross-sectional area, the shape, the volume of the cube. Now it's water, it's not solids. So something has changed, but it has nothing to do with the weight. It has to do with the cross-sectional area, and because of that, the pressure has decreased. So write it however you want, as long as you mention these two. And let's go to this part. Now ice melts at temperature of 0. We know that this is the melting point. And on the axis, sketch how the temperature of the ice cube changes as it rises from a temperature of minus 10 to a temperature of 20. Now remember that graph when we were trying to follow up with what's going to happen from less than something in minus to 0 to something to 100 degree and so on. Let's do that, but only from minus 10 to 20. So let's think about it here. At minus 1 until, let's say here, what's going to happen to the ice? It's still freezing. The ice is still ice as long as we are less than in a temperature that is less than minus 10. So the time goes, this axis is for the time, so the time goes and the temperature of the ice is increasing, however, it's still ice. So we're going that way. Don't come here, because this part here is all about time going in minus, يعني reversing the time. That's quite bizarre, I would love to have a time machine, but here it's not gonna work. So let's go to the only the positive side of time. But in temperature, this is the temperature here. This is the temperature axis, so we can go minus and positive, but for the time axis, you only can go with the positive part, only here. Yeah, so getting back to here, at the beginning, from minus 10 to 0, to the melting point here, to the melting point, what's going to happen here is that the temperature of the ice is going to be increasing, because it's like the cube is gaining energy and it's storing, the ice is storing the energy in its kinetic energy store, and its kinetic energy is directly related to temperature. So rising the kinetic energy is another way of saying like rising the temperature until this point where the temperature stops from rising. No rising in temperature here. But where is my energy going? All of the energy here is going to change the state of the cube. Now the cube starts to melt because all of the energy is going to break or at least weaken the bonds between the particles until one point where all of the ice becomes water. Now here it's all ice, just rising the temperature. Here starts to melt and it's going to be that no temperature rising here. You see, this is zero temperature, this is 0 Celsius, but the time is going and no rising in temperature until one point where all of the ice becomes water, and then again we will witness rising in temperature with time. Because what? Because all of the ice becomes water here, and so the water and like it's going to act normally where the energy is going to transfer to the kinetic energy store, and the particles are going to be vibrating more, so rising the temperature more until the melting, until the boiling point. But here we are concerned only until the 20%, 20 Celsius. So this is the whole thing. And it's a little bit messy. Let me clean up here, because the only part you need is, I'm almost done, bear with me. So yep, that's how it is. That's the answer for this question. If you draw it that way, I think you're gonna get them full mark. But it's gonna be nice if you add some parts, like, yeah, like this one is going to be ice, this one is going to be ice with water, and until here all is water. This one is, and this one here, and this one is 0. This one is perfect. Now it is perfect. I hope you understand that. So let's go to the next one. Now saying like explain the changes that occur when a solid melts. Reflect to particles in your answer. This one is asking about the particle theory or the kinetic theory. So what happened exactly here when, yep, let me change the color. Let's get back to this. So what's happening when the temperature is rising, when the time is going and we gain some thermal energy, but the temperature is not rising. It's changing its phase, right? The ice cube is melting. So we're talking about this part. This part, when we don't have any rise of temperature, what's happening? That's the question. Explain what's happening when the ice is melting, the change that occurs when the solids melts. So again, here you have 2 marks. 2 marks, so 2 important points. Number 1 is you have to mention that the bonds, is that color clean for you? Clear, I mean? Or let's change it to something else. Yeah, better. Bonds between particles are weakened or broken. You can say broken, or you can say weakened, or you can use both. This is number 1. All the energy is going to be working on breaking the bonds between the particles instead of rising the temperature, because now we're going through a change of state. Now the second thing, because of the breaking of the bonds between the particles, what's going to happen to these fixed positioned particles? You know, in solids, they have, the particles are arranged in a way that is kind of regular. They are regularly packed together. So now it's not going to be the same because the bonds between them are weak. So the second thing that's happening here is that the particles, let's say particles go from vibrating around or about fixed positions, which is the case with the solids, to sliding past each other. This is the second point. You can say that, or I prefer this third one. 2 points out of these three are going to be enough, but you can use this or this, up to you. You can say that the particles get a little bit farther apart from each other. Particles, let's make it more simple, get farther apart. Now they don't have the same arrangement they used to have when they are solids. So we're talking about changing from solid to liquid. And these in solids, the particles in solids, they are close to each other, they have strong bonds, and so we're going to talk about this changing because of the thermal energy they gained. And don't mention the kinetic energy here, because kinetic energy is directly related to change in temperature, but in this case here, no change of temperature is happening. The only thing happening here is change of the phase of the state of the matter. Not because when you talk about any change of kinetic energy, it's kind of you're hinting of a change of temperature, and we know that this is not correct here. That's why only talk about the bonds between the particles being broken or weakened and the particles being a little bit farther from each other. Now you can move freely. So use whatever language you feel like using, but as long as you're hovering through or around the same thing. And we're done with this question. Good luck.